Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Today I am going to discuss physical properties. Physical properties of haloalkane and haloarene. Last class I have discussed its preparation. Now I am going to discuss physical properties of alkyl halide or aryl halide. Alkyl halide are colorless when pure. However, bromides and iodides develop color when exposed to light. Many volatile halogen compounds have sweet smell. This is very characteristics. Melting and boiling points. Methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes are gases at room temperature. Higher members are liquids or solids. Again, you listen. Methyl chloride, methyl bromide, and ethyl chloride, and some chlorofluoromethanes are gases at room temperature. Higher members are liquids or solids. As we have already learned, molecules of organic halogen compounds are generally polar. These compounds are polar. Due to greater polarity as well as higher molecular mass as compared to the parent hydrocarbons, the intermolecular forces of attraction means a dipole-dipole moment and van der Waals forces are stronger in the halogen derivatives. This point is important. Again, you listen carefully. Due to greater polarity as well as higher molecular mass as compared to parent hydrocarbons, the intermolecular forces of attraction. Intermolecular forces of attraction means dipole-dipole moment and van der Waals forces are stronger in the halogen derivatives. That's why the boiling points of chloride, bromide, and iodides are considerably higher than those of hydrocarbons of comparable molecular mass. The attraction get stronger as the molecules get bigger in size and have more electrons. The attraction get stronger as the molecules get bigger in size and have more electrons. The pattern of variability of boiling points of different halides. Actually, this attraction, I told you the attraction gets stronger as the molecules get bigger in size and have more electrons. And on this basis, boiling points differ to boiling points of different halides differ to each other. For the same alkyl group, the boiling points of alkyl halides decreases in the order. That is, Ri is greater than Rbr. Rbr is greater than RCl and RCl is greater than RF. This is important point. Question is asked. For the same alkyl group, the boiling points of alkyl halides decreases in the order. Ri is greater than Rbr, Rbr is greater than RCl, RCl is greater than RF, where R is alkyl group, I is iodine, iodine, bromine, chlorine and fluorine. Ri is greater than Rbr, means alkyl halide is alkyl iodide is greater than alkyl bromide, or you can tell that iodide halide is greater than bromide halide. Bromide halide is greater than chloride halide, and chloride halide is greater than fluoride halide. Means fluoride halide is a least a boiling point, and Ri means alkyl iodide is the highest, and fluoride these things halide is least. This is why it happens. Already I told you, again I am telling you, this is because with the increase in size and mass of halogen atom, the magnitude of van der Waals forces increases. When van der Waals forces will increase, means attraction will increase, then what will happen? First, size has increase in size, and mass of halogen atoms both has increased. Then third things, its magnitude of van der Waals force also increases. That's why boiling point increases. Okay. Now the boiling points of isomeric haloalkanes decreases with increase in branching. Again, this is the important point. The boiling points of isomeric haloalkanes decrease with increase in branching. For example, 2-methyl-propane has the lowest boiling point among the three isomers. Okay. First isomer, that is a CH3, CH2, CH2, CH2. 1, 2, 3, 4. Okay. Br. This is actually 4 means butane. 4 carbons are there in this compound. Then all are, you can say, butane, butyl bromide, or you can tell 2-bromo. That is a compound name directly I am telling you, 2-bromo, 2-methyl-propane, 2-bromo, 2-methyl-propane. Here also total 4 carbons are there. Okay, but its name is 2-bromo, 2-methyl-propane. Because 3 carbons continuous straight line is there, and after that from the middle carbon 1 methyl group, and only from that bromine is also attached. Correct? Means central atom out of 3 in the middle, methyl group is attached and bromine is also attached. Correct? Then this is also actually butane isomers. In that, bromine is substituted with one hydrogen. Okay. Then three are there. First I told you CH3, CH2, CH2, 4 CH2, and the end Br is there. First is CH3, after that CH2, CH2, CH2 and Br. Then this is this you can tell bromobutane. Bromobutane. Okay, and second is CH3, CH2, CH3. First and last is CH3. And bromine is now attached with second carbon. Then see, this is the second isomer. And third I told you already that CH3, CH3, and from the middle one CH3 and one Br is attached. Then these are the 3 isomers. Then these 3 isomers have same molecular formula. All 3 are isomers, same molecular formula. Structure is different. In first case, that bromine is attached with the first carbon. Or you can tell that last carbon Br is attached, CH2Br. CH3, CH2, 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 Br. Its molecular, its boiling point is 375 Kelvin. 375, first isomer. Now, for second, when bromine is attached to the second carbon, a straight line, mean a normal position, then its boiling point is little less, 364. And now in the third isomer, when it is branched, one CH3 is attached with the central, total 4 is only there, and bromine is also there at second carbon. Then now its boiling point is further less. Then this I told you, the boiling points of isomeric alcohols, this haloalkanes, decrease with the boiling points of isomeric haloalkanes decrease with increase in branching. In third case, branching is there. Then this I have discussed. Boiling points, actually this question is asked. Why this happens? Now you listen. Boiling points of isomeric dihalobenzenes are very nearly the same. Okay, boiling points of isomeric dihalobenzenes are very nearly the same. However, the para isomers are high melting points. Boiling points of isomeric dihalobenzenes are very nearly the same. However, the para isomers are high melting as compared to their ortho and meta isomers. It is due to symmetry of para isomers that fits in the crystal lattice. This reason why these para isomers are high melting point as compared to their ortho and meta isomers. Then it is due to symmetry of para isomers that fits in crystal lattice better as compared to ortho and meta isomers. Correct? And example I am telling you. this benzene with benzene ring, 2Cl is attached. 2Cl is attached. And second one, 2Cl is attached, but in the first case, first isomer, it is at ortho. Cl with respect to Cl, second Cl is at ortho, and its boiling point is 453, and second isomer, it is at meta position with respect to first chlorine. Now its boiling point is 446, and 453, 446, it is less. And third is the you can say at para. Third is at para with respect to the first Cl, it is at para. Then now its boiling point is 448. Then boiling points are roughly close, 453, 446, 448. But melting point for first isomer means at ortho position, it is 256. Second is less, 249, and third, second is actually at meta, it is 249, but here you can see third at para position, it is very less, 323. Okay. Now I will tell about density. Bromo, iodo, and polychloro derivatives of hydrocarbons are heavier than water. This is again an important point. Bromo, iodo, and polyhydro derivatives of hydrocarbons are heavier than water. The density increases with increase in number of carbon atoms. First, halogen atoms second, and third is atomic mass of the halogen atoms. Okay. Three things. The density increases. Why increases density? The density increases with increase in number of carbon atoms first. Second, halogen atoms. And third, it's a number of halogen atoms. First I number of carbon atoms, second number of halogen atoms, and third atomic mass of the halogen atoms. Due to these three reasons, density increases. As for example, that normal, you can say C3H7Cl. C3 means propane, normal propyl chloride. A straight line, you can tell normal propyl chloride C3H7Cl. Its density is 0.89. And other, now C3H7Br, now it is a bromine, then its density is now more, 1.335. And next, normal NC3H7I, N means normal, straight, now it says more, furthermore, 1.747. Now you can see this I told you, chloride, bromide and iodide. Okay, means propyl chloride, propyl bromide, propyl iodide. Now next I am telling you CH2Cl2. Now 2 chlorine is attached. with carbon. Then now its density is 1.336. And next is CHCl3. Now 3 chlorine attached. Then now density is 1.489 more. Now CCl4. Here 4 chlorine is attached to the carbon. No hydrogen, all chlorine atom. And now its density is highest, 1.595. Okay. And see how it has increased with the number of chlorine atom. Density, you know, density is the mass by volume. Density is equal to mass by volume, means gram per ml. Gram per ml. You are comparing, you can say, mass of 1 ml of each. Then now mass is increasing per ml of all these 3 example. 3 plus 3, 6 example I have given. Okay. Now come to the solubility. The haloalkanes are only very slightly soluble in water. In order for a haloalkanes to dissolve in water, energy is required to overcome the attraction between the haloalkanes molecules and break the hydrogen bonds between water molecules. Okay. Again you listen, this is important. The haloalkanes are only very slightly soluble in water. In order for a haloalkanes to dissolve in water, energy is required to overcome the attraction between the haloalkane molecules and break the hydrogen bonds between water molecules. Less energy is released when new attractions are set up between the haloalkanes and the water molecules, as these are not as strong as the original hydrogen bonds in water. As a result, the solubility of haloalkanes in water is low. However, haloalkanes tend to dissolve in organic solvents because the new intermolecular attraction between the haloalkanes and solvent molecules have much the same strength as the ones being broken in the separate haloalkanes and solvent molecules. Okay. Again I am telling you because question is asked, less energy is released when the new attractions are set up between the haloalkanes and the water molecules, as these are not as strong as the original hydrogen bonds in water. Okay, in the beginning it is more strong, but with water it is less. Okay, less energy is released when the new attraction, means here with water, less energy is released when the new attractions are set up between the haloalkanes and the water molecules, as these are not as strong as the original hydrogen bonds in water. Correct? As a result, the solubility of haloalkanes in water is low. However, haloalkanes tend to dissolve in organic solvents because the new intermolecular attraction between haloalkanes and solvent molecules have much the same strength as the one being broken in the separate haloalkanes and solvent molecules. Here no differences in energy, almost the same. Okay. Have much the same strength. Are also, like dissolves like. This I have told about the solubility. That solubility means haloalkanes are only very soluble, very slightly soluble in water. In order for a haloalkanes to dissolve in water, energy is required. This is the main thing. Energy is required to overcome the attraction between the haloalkanes molecules and break the hydrogen bonds between the water molecules. Energy is required. Less energy is released. Less energy is released when new attractions are set up between the haloalkanes and the water molecules. Less energy is released. This is important point. As these are not as strong as the original hydrogen bonds in water. Okay. Now I am going to discuss chemical reactions. Chemical reactions of haloalkanes. The reaction of haloalkanes may be divided into the three types. First, nucleophilic substitution. Second, elimination reaction. And third, reaction with metals. Their reaction can be divided into these three important parts. First, nucleophilic substitution. Second, elimination reactions. Third, reaction with reaction with metals. Then these are the categories. In that you can say reaction of alkanes depends. It can be categorized only in these three groups: nucleophilic substitution, second elimination reactions, third reaction with metals. Then first you come nuclear substitution reaction. Nucleophilic, also you can tell nucleophilic substitution reaction. Okay, first type, first category, nucleophilic substitution reactions. In this type, this is very, very important. Just to listen carefully. In this type of reaction, a nucleophile acts with haloalkanes. Means haloalkanes means substrate, you can tell. Substrate. And nucleophile, already I told you, nucleophile, it is denoted by Nu. Capital N, small u, nucleophile, Nu, having negative charge. Okay, having negative charge, one pair of electron and negative charge. It is represented like that way. In this type of reaction, a nucleophile acts with haloalkanes having a partial positive charge on the carbon atom. On the carbon atom bonded with halogen or bonded to halogen. A substitution reaction takes place and halogen atom called leaving group. Hydrogen atom is called leaving group, departs as halide ion. This is important kind. Substitution reaction means one will go and in its place other will come. Okay, there is a substitution reaction means here when nucleophile and halide comes together, reacts to each other, a substitution reaction takes place and halogen atom called leaving group departs as a halide ion. Departs as halide ion. Since the substitution reaction is initiated by a nucleophile, it is called nucleophilic substitution reaction. Then reaction is very easy. Nu1 minus, always you write for nucleophile, Nu plus, now halide you are writing CX. There is a bond between C and X. In general way, X is halogen atoms. Then X is negative, X is delta negative, some negative charge it has, halide. And carbon is delta plus, means positive charge. Carbon has positive charge, little positive charge, X has little negative charge. And little positive charge, little negative charge is shown by delta. Delta positive, delta negative. Then now see nucleophile Nu plus this CX. C is positive, X is negative. Then now X is also negative, Nu is also negative. Then substitution reaction will take place. Nu will go in the Nu will go to the you can say Nu will replace X in a simple way. Nu will go there and X will go out and its place and its place X place Nu will attach. Okay, the new bond will be formed CNU and X will be displaced. Okay, X will be displaced as X minus, means halide ion. Then very simple reaction is there. Nu have one negative charge plus halide means CX, then X will be replaced by Nu and X will leave as chloride halide ion, X minus. It is one of the most useful classes of organic reaction of alkyl halides, in which halogen is bonded to sp3 hybridized carbon. Here carbon is in sp3 hybridized state. Here carbon is sp3 hybridized. Hybridization is sp3. Okay, this is called sp3 hybridized carbon. And in this sp3 hybridized carbon, this reaction took place. The products formed by the reaction of haloalkanes and some common nucleophiles I will tell you as examples. Then reagent, as for example, NOH, this is the reagent. It will react with nucleophile. Reagent as for example NOH or KOH. Now nucleophilic or nucleophile you tell Nu. Nu we can represent as OH1 minus. And now if you can say a reaction will take place. If a reaction will take place with alkyl, then what will happen? Then in alkyl R will be certain. Okay, Rx reaction is Rx plus Nu. R and X bond is there, Rx plus Nu. Then now already told you reaction will be that RNU, product will be RNU, because X is replaced by Nu. In the place of X, Nu came, RNU plus X minus. It went as a halide. Then now here that I will tell that these things Nu, nucleophile. Who are the nucleophile? Name of the nucleophile. Then OH. These are the nucleophile. This OH 1 minus H2O R-O 1 minus I 1 minus NH3 1 minus R-NH2 1 minus R-NH. These are nucleophile. Okay. Then reaction I can understand now very easily. If suppose it is just like reagent is reagent, also you can understand. If NOH is reagent and nucleophile is NU, then substitution product RNU. Substitution product RNU means ROH. Actually, this NOH will give you OH minus. That OH minus will go to the R. Means RNU. Then here NU is equal to OH. Then it will form substitution product will be ROH. Similarly, if H2O is there, then that will also provide you OH. Then this will also give you ROH. Then this ROH is called alcohol. It will form alcohol. Like that way, NaOR, it will give you OR. It is a reagent. Suppose NaOR is reacting with RNU, not reacting means this NaOR plus alkyl. Okay, alkyl means alkyl halide. NaOR plus alkyl halide. If both will react, then what you will get? You will get ROR dash. Then this OR dash from is actually nucleophile. OR 1 dash you can tell. Then this OR from where it came? Then it came from the NaOR dash. Like that way, suppose NaI is there, sodium iodide, plus suppose halide is there, then this alkyl halide. Then again same way here NaI will give iodide, I minus, as a nucleophile, and product you will get Ri. Okay. Similarly, if ammonia is reacting with alkyl halide, then it will give RNS2. NH3 will provide NH2 and it will form RNS2. This is the primary amine. Similarly, if NHR is suppose nucleophile, NHR dash, and if it will react with alkyl halide, then now it will give RNHR. 2 R is attached with nitrogen, 2 R and R dash is attached. Then this is the secondary amine. Similarly, if R dash NH is reacting with R dash NH, if it is reacting with alkyl halide, then now this R dash R double dash NH, 2 R is there, then it will provide R dash NH will react with alkyl halide, and now 3 R will attach to the 3 R means R dash R double dash will attach to the alkyl alkyl. Then now 3 means 3 R. Now it is just attaching with nitrogen. Then it will be tertiary amine. Then like that way CN, RCN is there, RCN plus alkyl halide. Then halide will go replaced with cyanide. Then it will called RCN. RCN is called cyanide or nitrile. Other name is nitrile. Very simple reaction. Alkyl halide plus KCN. Then halide will replace with CN. Every case same thing is happening. Then now it will form RCN, that is called nitrile, also called cyanide. Like that way, if AgCN is reacting with alkyl halide, then now halide will replace with CN and it will form RNC. This is called isocyanide. CN is called cyanide, but NC, when N will make bond with alkyl N, then it is called isocyanide. But if C is making bond with R, means alkyl, then it is called cyanide. If C is joining with alkyl carbon, then cyanide. And when N is joining with alkyl carbon, it is called isocyanide, also called isonitrile. Like that way, if KNO2 is reacting with alkyl halide, then halide will be replaced by NO2 and it will form RONO. Actually, NO2 will join with O. O will join with carbon of alkyl, RONO. It is called alkyl nitrite. Okay. Like that way, if AgNO2 is there, AgNO2, silver nitrite is there, then silver nitrate plus alkyl halide, then in the place of halide, NO2 will come. Then now it will form RNO2. Now N will join with R. N will join with carbon of alkyl group, alkyl R, N. Then now it is called nitroalkane. But see, there first case KNO2, when KNO2 reacted with alkyl halide, then NO2 is also there. But their difference is that their NO2, that NO2 is joined through O. O has joined with R, alkyl group. Okay. O, but here N is joining, that is the difference. When N is joining, that is called nitroalkane. RNO2, both NO2 is only there, but difference is that in the first case that O has joined with carbon of alkyl, and here N has joined with carbon of alkyl. Then first case it was called alkyl nitrite. But here in second case, when NO2 is joined, it is called nitroalkane. Like that way, if ester is joining RCOOAG, suppose this is the ester group RCOOAG. Okay, this is the salt. Then RCOO, that is the minus. Then this will be replaced by halide. RCOO will join. Then now it will form ester. This was RCOOAG, it was the salt. Then from this salt, it will provide RCOO. And this ion will be replaced by halide ion, anion, replaced by halide anion. And this RCOO 1 minus will attach with the alkyl group, alkyl halide there. Then it will form ester, R-COOR, or simply RCOOR, you can tell. COO, RCOO is called ester group is called ester. Like that way, lithium aluminum hydride, it will provide hydrogen, and that hydrogen will be replaced by halide, and it will be RH, means hydrocarbon. RHCl went and its place H came, then it will form RH, hydrocarbon. Similarly, R-M plus, this is also salt, R-M plus, then it will provide R-1 minus, then it will react with alkyl halide, halide will be replaced by now R dash, and now it will be RR dash, means alkane. It forms alkane but higher carbon. And this I have told many reaction based on nucleophilic substitution. These reactions are called nucleophilic substitution of alkyl halide. Here alkyl halide is RX, and Nu means nucleophile, which is negatively charged. Because both are negative, halides are also negative, nucleophile is also negative. Hence easily substitution can take place, it can be replaced easily. Groups like cyanides and nitrides possesses two nucleophilic centers and are called ambidentate nucleophiles. Already I have discussed. Okay, groups like cyanides and nitrides possesses two nucleophilic centers and are called ambident nucleophiles. Actually, cyanides group is a hybrid of two contributing structure, cyanide, and therefore can act as a nucleophile in two different ways. One can join through CN, other can sometimes conjoin with N. CN may convert to NC also. Okay, sometimes C and N triple bond is there, then carbon has negative, and sometimes it can make double bond C and N double bond. That time nitrogen will have negative. One time carbon is negative when triple bond. When double bond C and N, that time nitrogen will be negative. Okay, a carbon will have one pair of electron. Then where negative is there, only from there it will substitute. This is actually linking. Then nucleophilic, here I told you that this actually cyanide groups is a hybrid of two contributing structure and therefore can act as a nucleophile in two different ways. That is a linking through carbon atom resulting in alkyl cyanide and through nitrogen atom leading to isocyanides. Similarly, nitrite ion also represents an ambient nucleophile with two different point of linkage. Okay, ONO, O is negatively charged and other O is double bond. Then it will not join with double bond, it is strong. It will join with O. O and N single bond is there and O is negative. Then from that oxygen which has one negative, it will join from that. Then nitrite ion also represents an ambident nucleophile with two different point of linkage. The linkage through oxygen results in alkyl nitrite, while through nitrogen atom it leads to nitroalkanes. Already I have discussed. Now this substitution reaction, that reaction mechanism I want to tell you because question is asked. This is called SN1 and SN2 reaction. It is of two type, SN1 and SN2. Then here SN, capital S, capital N. S means substitution, N means nucleophilic substitution. S means substitution, N means nucleophilic. And what is the meaning of 1 and 2? then you know if it is a 1, then it means this reaction will be of first order, kinetics, first order reaction. And if it is SN2, then it is of second order. Always remember. Only in the beginning I am telling you, many times question is asked. Then how will you differentiate? Then SN1, 1 means first order reaction. Kinetics, you have already I discussed chemical kinetics. First order reaction means it will react, it will the reaction, rate of reaction will depend only on one reactant. Even maybe two reactant, but rate of reaction will depend only on one reactant. And in SN2, and here again you understand, SN1 means first order, but in two-step reaction will take place. In a two-step, correct? And reverse of this, that is the SN2. That in SN2 already told you the second order. 2 means second order. Rate of reaction depends upon both. If two reactants are there, then rate of reaction will depend upon both reactants, A and B, as for example. Then that is called second order. But this second order reaction will take place in one step. But first order reaction will take place in two steps. Okay, this you keep in mind. Only in the beginning I have told you. Okay, first order reaction will take place in two steps, and second order reaction will take place in one step. Means SN1, it will take reaction in two steps, and SN2, it will take place, reaction will take place in one step. Okay, then this SN2 one, this I am telling you mechanism. Okay, SN2 because it is of one step, that's why I am telling you. Okay, then here this reaction has been found to proceed by two different mechanisms. Okay, then first I will tell you substitution nucleophilic bimolecular reaction. Bimolecular, 2 means bi, bimolecular, and other will be substitution reaction monomolecular. Then now SN2 I am telling you, the reaction between methyl chloride and hydroxide ion, very simple reaction. CH3Cl means alkyl halide plus hydroxide ion, OH minus means NOH. NOH will provide OH minus. Then simple reaction is there. Reaction is very easy. That Cl will be substituted by OH. It will form CH3OH. CH3OH. But what will happen? Final will be CH3OH means alcohol, methyl alcohol, and Cl will be relieved. It will leave chloride ion. Then here what is actually mechanism? That OH will come near the OH ion, which negative ion will come close to the carbon atom CH3, then that C is there, then OH will come near the carbon, and it will means it is approaching, OH is approaching to carbon atom, and it will make first it will make a weak bond, ... you can write, and Cl, which was now somewhat strongly bonded, now it will become weak. Now in this things intermediate state you can write now carbon Cl bond ... As soon as OH approaches carbon, same moment Cl will begin to leave, its bond will be begin to weak. Why? Because OH is also negative, Cl is also negative, then repulsion will be more. Due to that repulsion, now Cl bond will be weak. Then intermediate state you can show OH also, Cl also. Both bond you can show, but bond you have to write dot dot dot. For OH and C bond is dot dot dot, and C and Cl bond also you can write dot dot dot. In a bracket you can write, that is intermediate. And now slowly and slowly as the OH bond will become strong, Cl will leave, and finally it will give CH3OH and plus chloride ion. Okay, then this I have told you mechanism. Now I will continue this reaction in details. Okay, SN1 and SN2. Today, now I am stopping only here. Thank you.